Okay. Now we are going to, after we showed how we are going to do our calculations, how are we going to inspect this QO total. Okay, so we are going to do that in Python, Jupyter Notebook, because it's relatively straightforward to make the plots. So I have a file called gas lift 2 wells, and let's see what do we have there. Okay, so I'm importing the libraries. I need NumPy to for creating the vectors. I need it to define this function. I need to this optimize. I don't really need it. I think I copied from before, and then I need plotting. Okay, this I don't think I need. Then I define this function that will be one for each well, right? You have A, B, C, D, E, as I explained before, and you need also the Q gas injection, and you simply compute that polynomial, and that's actually I fit it to a fourth degree polynomial. This is the data for both wells. You have all the A, B, C, and D, and E for both wells, and you have oil price and gas price um, that if we are going to make later on, we are going to change the objective function and we're going to do optimization. Okay, so let me just copy these things to the PowerPoint. Yeah, let's see later what happens here. So this is, I call it brute force computing all combinations. Okay, we say we want 100 points, and that means 100 points in these divisions of Q gas injection 1 and Q gas injection 2. I want 100 points on each. That means that the multiplication will be 10,000 combinations, right? Then I define a maximum range of gas injection. Okay, and this is 200,000 standard cubic meter per day. Um, then I say, well, now create a vector, this vector that I was mentioning here, these two vectors, and I say create uh, that vector from 0 all the way to this maximum, and with this number of points. And the same thing for well 2. Now I create some vectors, some empty vectors to save the results. Okay, for the oil total, the gas injection total, because I know that will be a constraint, and the revenue. Okay, then I go for each combination. For all 1G, this is taking one element, okay, in that vector, one by one. This is taking the element in the second vector of gas injection rate, okay, and then is calculating using this function. Um, Let me just copy this and use it in Excel. In Okay, number of points. These are the two vectors. Okay, so from 0 to the last one will be 200 in this case, and you have 100 points. It will be Q gas injection 1 and Q gas injection 2, this guy here. Okay? Then these are some empty vectors I have for the results. Okay? Then I say for each element, okay, that means for each, let's say, let me change the color. Okay, each element, I go for one, and then I go to all of the other elements. This one with this one, 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 until I reach the end. Okay, and what I'm going to make, I'm going to calculate with Q gas 1 being, and this could have been done in a more efficient way, I see now, but this one being 0 in this case, okay, you're going to change all of these 0 to 200 to until I reach to 200, okay, and I'm going to compute the oil produced by, so that means I'm going to go to the curve of well 1, Q oil and Q gas injection, okay, and the well 2 curve, which is Q oil also in Q gas injection. Okay, and with this one being 0, okay, with the first element, okay, and I'm going to go and I'm going to compute for all these elements. I'm going to go 0, find out what is the rate. This one, find out what is the rate, and I'm going to sum those two. For example, for the first combination, I'm going to sum up the production of oil of well 1 and 2, and I'm going to append it to this result vector. I'm going to append it also to the gas injection, and I'm going to calculate also the revenue, okay, which the revenue means it's the oil production times the oil price, how much I can sell this oil for, minus how much does it take to buy the gas, okay, which you have a price of gas, how much does it cost, and a minus sign. Okay, and the revenue, I'm going to express it in 1 e to the 03 thousand US dollars. Okay. So you see what's happening here. Essentially, I'm going through all of this grid and I'm calculating these points, but I'm not only calculating oil rate, okay, but I'm also calculating the gas injection, which is simply the sum of the gas, these two guys, okay, these two elements in this vector, this and this one, and I'm also calculating the revenue with the oil rate and the gas rate. Okay, and it's like I'm doing my integrated asset modeling, all of it in my Python model. Okay, okay, let's go back to Python. Okay, then I'm going to create these color maps. Okay, and let's see here. I have two optimization variables. Okay, so I'm going to use one is if it's oil rate. That's what we are going to focus on now. One. So then you're going to assign objective, which is this vector, to revenue, and you're going to change the tag on the plot. And we're going to see now what this level means. Okay. If I say that is 2, then it will be revenue. Okay. The constraint, we are not going to talk yet about constraint, so forget about it for now. I'm specifying the plot size. Remember that essentially we have a vector with 100 points, right? But when we have this grid, essentially we have to repeat this value for all of these numbers. Okay, so we have to repeat it. And also we have to repeat it here, this value here and here. So at the end I need to have these 10,000 points. Okay, so that's why I'm using this syntax, okay, to create that grid. Okay, essentially it's repeating the value of x for all the values of y, okay, to be able to plot it. Otherwise, it doesn't know, the plotter doesn't know which value should I repeat, okay, or how should I arrange my grid. Then we're not going to look into contour now. We just want to plot, and we're not going to look at So let's keep this away from now. And what is important is just this sentence that I have here, this instruction that tells it to make a color mesh. Okay, that's this color plot of XY, which was the gas injection rate of well 1, Y1, YI, which is the gas injection rate of well 2, and of the objective function, which in our case is the oil rate. Okay, and just applying the labels. So after I have this done, I hope I will run all cells. Okay, it takes some time, but that's what it gave me. Okay, so you see, and that's exactly what I was showing. These are all combinations. For example, for 0, 0, gas injection well 1, gas injection well 2, I'm going to get almost 0. Okay, almost 0 production. Which, if we go back and check our E's means that I have 12 and I have minus 17. Okay, that means that I essentially this well doesn't produce. Okay, it has a production of 0, and this well essentially produce very low. Okay, I think it should be 17. Okay, let's change it to 17. Oh, wait, let's keep it minus 17, but I think it should be positive. But essentially it means that it doesn't produce. Okay. So, but after, if I start injecting more and more gas, okay, then let's say I keep this one fixed, I inject more and more gas, I'm actually increasing. You see the amount of oil that I'm producing. I'm increasing to 150, around 200, between 100 and 150. Okay. If at the same time I increase also the gas injection rate of well 2, I also increasing the total production. Okay, so let me take a snapshot of that. And I have, it looks very smooth. I don't see any, I see a few squares you see here on the pixels, but essentially looks very smooth because it has 10,000 points. It has a lot of points. Okay, so if you were going to say, where is the maximum here? That's my objective function. I want to optimize. Okay, where is QO total maximum? Okay, you see this diagram, you say, well, is where I have the lightest yellow. Okay, so it will be someplace here according to my, like on the with the naked eye. Okay, so it might be someplace around these two, okay, which is 100, sorry, 70. Okay, I use X and Y. I use X first, which is Q injection well 1. Maybe that will be 76 and will be around 100. Okay, okay, and it's around is this is like 225. Okay, Q oil total is 225 around. Okay, standard cubic meter per day, and Q gas injection one it's around 76,000. Okay, and Q gas injection 2 is around 100, and well 2 is around 100. Okay, so we made an observation, we look how the surface looks like, and as we say, well, if you're going to operate, that's what you should that's where you want to operate. Okay, now we also have another we can make a contour plot, another way to plot this data. Okay, and the contour plot is a bit more, is a bit different. Okay, the contour plot, the main intention is that I'm going to join all points that have join all points with a line that have the same Q oil total. Okay? That means, and that is going to give me, I'm going to see now, but essentially if we try to make it here, which we are not going to be very successful, okay, would we try to join all of these that have, for example, are green, okay, maybe all of these that are also a bit more blue, and this has, for example, Q oil total of, let's say, 150, okay, and then yeah, this one might have a Q total of 100. Okay, so this is a different way to observe the same data. Instead of using a color, you simply look at the contour plot and you join all of those points with a line that have the same QO total. Okay, and for points which are a bit more inside, it looks maybe something like that, okay, which are closer to, okay, and that might be 200, okay, Q oil total. Okay. And it's contour because it's like a ISO value line. Okay, it's a ISO value line. And so let's make that was the part that I deactivated on the Python script. Contour plot of objective function. So to plot the contour plot, I have to provide okay, I have to provide contour plot contour, the same x, y, and the same objective. Okay, but now I have to give how many levels I want. Okay, and levels mean how many of these iso lines that I have been plotting here. Okay, and then I'm saying that put a label, and I want you to show with just no decimal points. Okay, simply with one value. So let's run this one again. Okay, and I obtain this one. Okay, you see it's exactly the same chart that I had before. Okay, that's actually the control line, so this one I can erase. Okay, it's exactly the same, but now I have some control lines that they tell me where the function, this is the QO total, okay, it's not the injection. This is just for this combination. I have, this map is showing just the value of oil that I'm producing. Okay, so you see ISO lines, all of these, they will have the same um, the same value. So now that's fine. I have found my maximum, okay, which should be someplace here. I think according to, I made a mistake, might be someplace here, 100 and 100, not 175. Let's increase that a bit. Well, I cannot change it. So let's put here, I believe. Okay, but as you can see, it's very, you know, prone to error. Actually, it should be more or less here. Okay, so now I'm going to ask you what happens with the constraint. Remember, with this constraint we have here, that we have a total gas to inject. Okay, let's see the effect of the constraint. Let's take the same chart, and I'm going to repeat it here, and I'm going to say what is the constraint. Okay, what about this constraint that QO, sorry, not QO, but Q gas injection total has to be the sum of the Q gas injected in well 1 and the Q gas injected in well 2 has to be less or equal than, I knock my microphone. Let me see if it still records. Yeah. So the sum of the injection gas that I inject on well 2, gas injection, and the gas lift gas that I inject in well 2 should be less than a total. Okay, so how, if that total, let's say, is 140, okay, that I should always use units, remember, always use units. So how will that look like on this chart? Okay, so let's go to the extreme. Only one well is producing. Let's say well 1 is producing and well 2 is not producing. So well 2 will be 0, but well 1 will be 140, okay, which will be maybe someplace here, right? And in the same thing here, if these are the extremes, okay, these are only well 1 with gas injection, with gas lift, not gas injection, but gas lift, and this is well 2, only well 2 with gas lift. But what happens with everything in between? Okay, remember we are calculating this variable. We have it in our in our um, in our um, in our Excel sheet, in our Python script. Okay, but what will happen is essentially you have this line. Okay, because you have is like x plus y are equal to, if I make it on the extreme, that is equal to a constant. Okay, that tells me that y is equal to a constant minus x. Okay, and how that chart, that plot looks like, that plot essentially looks like a straight line like that. Okay, and this is the line where Q gas injection total is equal to 140. Okay, if I was going to change it, let's say I make it bigger, 175, okay, then I will have another line doing something like that, the constraint. Okay, or if I make it smaller, like 75, then it will be a line like that. Okay, so now I ask you what is, and remember, now it's not equal, it has to be less than that. So all my feasible area is essentially, let me go use another color, it's essentially this area here, because it has to be less than that. That's my feasible area. That's feasible. Okay, what I call the feasible area. So where is the maximum going to be located in that area? If I was unconstrained, I already showed that this will be our maximum. Okay, unconstrained, that's the maximum. If unconstrained, okay, but if I'm constrained now, the maximum or the highest value that I have in all of these region, in all this triangle, it actually will be here. Okay, so that is my maximum if constrained. Okay, so that's the effect of the constraint that the constraint has on my, like my function, the 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 domain or the area of the function where the function is. Okay, in this case, if I had, for example, a gas injection, total gas injection, which was someplace here, okay, then my maximum will still be here. Okay, I can reach that global maximum, I can reach that value. Okay, that's combination. But due to the fact here that they are below, the line is actually below, I have reached that point, then this will be my maximum, the maximum possible that I can attain, okay, that I can achieve. So okay, let me just duplicate that slide, and now I'm going to just to do it on, I'm going just to do it again on Jupiter. So what we make, that's why I have this second contour, okay, because I want these iso lines for Q gas injection, okay, for the total gas lift injected. Gas injection, that's a term used for typically for injection in the reservoir, but gas lift injection, that's a different thing, and that's injected in the wellbore. Okay, and there you see exactly the same plot that we were discussing before. You have the objective function with the contour lines in black, and then you have these lines which are the constraint, essentially where I have 200 um, okay, total gas lift to inject, total gas to inject. Okay, so you say unconstrained, if maximum will be here, but if I'm now constrained, depending what's my level of constraint, I'm going to be here, or here, or here, or here. Essentially, you see that all of the maximum points, if I have a constraint like that in the total, so this is the total uh, gas available. Okay, you see all points are on that line. Okay, before we abandon this example, let's now change the objective function. Let's now say that the objective function will be the revenue. Okay, the revenue we have, remember, is the oil price times how much oil I get minus how much I spend on the gas. Okay, let me just remove the constraint for now, or we can keep it. Let's copy the same chart here. That was the original oil rate. And now what happens if we use revenue? You see the objective function change somewhat. Okay, the total oil rate changed. Okay, you see that the contour seems a bit different. Okay, and the values, of course, they are different. You're getting 100,000 in this region, 120, maybe $110,000. Okay, if you operate in these conditions. Okay, but you see the constraint is actually essentially uh, uh, okay, similar. The constraint in rate. Okay, so the change in objective function. Okay, here we have revenue and here we have oil. So now the next step is to take I have another example for you, which is two gas wells in a network. And here I have two gas wells, and I have a choke. Okay, for this gas well, I have a pipeline or I have a flow line, then I have a junction, then I have another flow line, then I have another choke, Then I have another well. I have a choke. This will be a choke, and then I have a flow line going, a pipeline going all the way to the separator. Okay, and here I have PR2. I think they're producing from a different formation. PR1. Here I have choke 1 and choke 2. Okay, so that's my system, and here the main intention is that each well produces some condensate. Okay, so you have CGR of well 1, I think that's 0. Okay, and CGR of well 2, that is non-zero, but I don't remember exactly how much it is. Okay, non-zero. So the main intention is to find, in this case, what we are going to make is simply say maximize Q gas total, okay, produced. So simply this Q gas that I have here, Q gas total, Q gas 2, and here I have Q gas 1, okay, which will be the sum of Q gas 1 plus Q gas 2. Then we're going to see what the constraints are, but I might have constraints in might be Q gas 1, okay, which has to be below a limit Q gas maximum due, for example, to sand production to avoid. Okay, so we have addressed this issue before. Okay, we have addressed this model before. We are going to use dry gas equations. Okay, you remember the equations QG, CR, PR squared, PWF squared to the power of n. We have the tubing equation, QG, PWF squared over e to the s minus PWH squared 0.5, okay, times C, missing the C, times CT. The flow line equation we were using was essentially Q gas P in squared minus P out squared 0.5 C flow line, and the pipeline the same. Okay, so we have solved this problem before. Okay, it's a network, everything, so every change I make on well 1 is going to affect well 1 is going to affect well 2 and vice versa. Okay, so I have to solve the system, not like I have done in the gas lift case where I assume both of them are totally independent. Okay, I can write this thing, but essentially the rate of the total rate will be a function of, okay, we write it, Q gas will be a function of both the delta P choke 1 plus and is also a function of the delta P choke 2. And we have solved this exercise in Excel before. Okay, so essentially you have, if we're going to make it as a function, if we're going to use a function, we have our network model. Okay, we have some system parameters. Okay, we have P separator, we have CR1, CR2, we have PR1, PR2, we have CT1, CT2, we have S1, S2, we have C flow line 1, C flow line 2, we have C pipeline. Okay, then we have also delta P choke 1, delta P choke 2. Okay, and at the end what we obtain is the rates, are the rates QG1 and QG2. Okay, so it's a function. I specify these two, delta P of the choke, and then finally I end up with, considering solving all of that system of equation, I end up with QG1 and QG2. Okay, we have solved this problem in Excel. Now we are going to solve it in Jupyter, simply because it's simple to plot. Okay, and yeah. So what? And we're going to make exactly the same plot. We're going to make a plot of delta P choke 1 and delta P choke 2. Okay, from 0 to a high number. Okay, 200 bar, I think. And we're going to make a map exactly the same that we have done here, and we have a color bar, what we have done before. We have a color bar of Q gas total. Okay, and we are going to make, for all of these, we're going to make that combination. Okay, so let's jump right through it, and we see, let's show you how I have made it in. Okay. I can close this one and I open this one. Just also note that we, even though we have some condensate, we have some liquid, we are using dry gas equations. Okay, so the condensate will have some impact on my IPR, on the TPR, and on the flow line, but we are neglecting that effect. Okay, we are saying the amount of condensate is so small that really doesn't make much of a impact on the pressure drop calculations. Okay. So then again, I call these libraries in this file. Okay. The main difference here, I need to add a library to solve. Okay, in this case, because I have is a couple system of equations that depend on each other. It's a system of equations I have to solve. To solve this, I'm going to use a Python. Okay, a Python solver. Okay, in Excel, we have done it through the solver, Excel solver, but now we are going to use this Python solver called is from SciPy and is minimize. Okay, so I'm going to repeat this slide simply to copy. I'm going to do a screenshot. Okay, and you see we have IPR, okay, giving you the rate or giving you the pressure if you specify the rate, or if you specify the pressure, it gives you the rate. Yeah, after that, you have the tubing, tubing giving you rate, tubing giving you P1 or P2. So all of these I have compound in wellhead performance relationship. Okay, what I do here, like what we have done in a previous lecture, we have PR, we specify the rate, QG of the well. Okay, then we calculate PWF. Okay, that's this part here. Okay, that's the first part. Okay, and then on the second, I'm providing the rate, PWF, and then I compute PWH, available pressure at the wellhead. Okay, I'm specifying rate. I'm moving from the reservoir to the bottom hole with the IPR, and then I'm moving from the bottom hole to the wellhead with the TPR. Okay, tubing P2 and PW, and then I calculate the pressure at the wellhead. Okay, I calculate that pressure. And if you remember this equation, this WPR should give you, if I compute Q gas and I PWH, okay, this should give you an equation like that. Okay, this should give you a behavior like that. When I have no flow, simply get the hydrostatic column, okay, which will be the reservoir pressure plus less deducting a hydrostatic column. But when I start to increase the rate, I have friction losses, and therefore that pressure becomes smaller and smaller. Or equivalently, if I apply this pressure to the wellhead, then I will get this pressure, then I will get this rate. Okay? And then I have done here something, another step, which means is vectorize. I'm using this NumPy library to vectorize such that if because I have two wells, so I want to apply that equation with actually with a vector. Okay, I want to apply BWR, PWH, okay, wellhead performance relationship. I want to calculate the wellhead pressure, and I want to use a vector PR1, PR2, and I want to use a vector of CR1, CR2, and I want to use a vector of N1, N2, a vector of CT1 and CT2, and so forth, S1, S2, and then the rates, Q1 gas 1 and Q gas 2. Okay, so in order to activate the function, to accept it, to apply it, for example, on just the all first elements, okay, it will take all of these first, and then it will take all of these second, and then it will simply give you out PWH of well 1 and PWH of well 2. Okay, you need to apply this to vectorize, so it will be enabled to take vectors. Okay, now let's go to the second part of the equations that I have prepared for you here. Okay, line, that's the equation that I showed you before, line P1, line P2. This is this quadratic equation that it's QG is C pipeline or flow line, P1 squared minus P2 squared to the power of 0.5, okay, square root of that. And I'm again vectorizing it just to be sure that I can apply that for any number of wells. Okay, and I'm vectorizing just line P1, which is if I have a pipe with 1 and 2. Okay, that's the one that calculate, and the flow is going on this direction. That's the one that if I have this, which is the case of the separator, right? I have separator pressure on my problem, and I want to go back here, and I want to go back here. Okay, So it's P1, finding the inlet pressure to the pipe. Okay, and I'm vectorizing it such that it will take, it's able to take a vector, okay, line P1. If I use CFL1, CFL2, okay, which will be the flow line for each well, the P2, P2 in this case will be just P of the junction. Okay, just I have one value, and then you have QG1 and QG2. Okay? And this will give you two pressures, pressure in of well 1 and pressure in of well 2. Okay? Then after that, I create this function that is the wellhead pressure required, okay, or is the pressure if I have my system like that, okay. This function is from here with the two rays that you specified, Q1, okay, I go back to P junction, okay, that's the first step here. Okay, with the pipeline, with the separator pressure, I go and I calculate this P junction, and then for each one of the wells, I apply this function, and I go back and I calculate here P, it will be discharge of the choke 2, and P discharge of the choke 1. Okay, so that's essentially what this is doing. So this is in 1 is calculating that pressure, and then in 2 is calculating this guy and is calculating this guy. Then next comes the error. Okay, you have to be able to solve in Excel. What we have done is that we say for any delta that is given, okay, so delta choke, maybe I'm going to just make another. Okay, so then I have remember I have my wells, okay, that they go up to the choke, this wellhead pressure 1, and I have here also wellhead pressure 2, okay. Then I have this system where I have my separator, then I have these two guys where I have the P, and this I call, unfortunately they are also called P wellhead pressure 2, but this is required, and P wellhead pressure 1 required, which is not wellhead pressure, but is essentially the pressure. Okay, and then I have here a choke. I have here this choke element. Here where I have delta P choke 1, and I have here delta P choke 2. Okay. So I have the first two, I have this equation, and I have this that gives me these two equations. Okay, and I'm specifying the choke opening that I'm using. So to close this system, I have to find Q1, Q gas 1, and Q gas 2 such that, so I say given delta P choke 1 and delta P choke 2, find the gas rates such that P wellhead 1 minus delta P choke 1 will be equal to P wellhead 1 required. Okay, that means this guy, this guy, and this guy. Okay. Okay. And Each one of them, they calculated with this required is calculated with PWH required function. This one is an input, and this guy is calculated with the WPR PWH function. Okay, and also I have for the other well, I have PWH2 minus delta P choke 2 will be equal to PWH2 required. Okay. And I want to drive those two to 0. So the way I do it, I simply bring everything to one side. Okay, so I make an error which will be PWH1 minus delta P choke 1 minus PWH required 1, all of that squared, plus PWH2 minus delta P choke 2 minus PWH2 required, and all of that squared. Okay, so let's summarize. Given these delta P's, okay, you have to find these rates such that this pressure, this minus this delta P gives this pressure. Okay, and also the same thing, this one minus this delta P gives this pressure. Okay, in order to combine all of that in one objective, like we have done in Excel before, we try to compress everything in the same cell. We simply bring this guy to the left to deduct from these two, and then we square it, okay, such that if this one is positive and this one is negative, it won't cancel each other. So all of them are both of them are squared. Okay, so that's exactly what is done here. So available, here you calculate PWH1 and PWH2. Okay, in this guy I calculate PWH1 required and PWH2 required. And in this guy, this is essentially this error, okay, the calculation of that error. Okay, just to summarize, we are now going to this, after the gas lift example, we went to this case where we had two wells that each one of them has a choke, okay? And our main intention here, each well is producing some condensate, and we want to see what is the opening of these chokes, or the delta P of these chokes, such that they maximize, okay, Q gas. Here we're going to see later, we're going to talk about revenue, or we are even going to talk about condensate, okay, which might look like a trivial problem, okay, because we essentially, you might think, well, if I leave all chokes open, that will be my maximum gas production, right? Which that makes sense. But with condensate, well, I need to choke one of the wells. I need to choke, for example, um, well 1, which doesn't have any condensate. Okay, and more importantly, I have some constraints that they are in the maximum uh, um, gas production of well 1, for example. Okay, so then I say, how do we solve this problem? First, we look at the model. We said we're going to use dry gas equations for all the parts of the model, and the model we can visualize it like we gave all model parameters, and here we need, besides that, N1 and N2, okay, for the inflow, IPR, tubing, TPR, we have the flow line, and then we have the pipeline. That comes into a network solver where I also input the opening of the choke, the delta P of the choke, and then I calculate the equilibrium gas rates of well 1 and well 2. We have done this before in Excel, but now we're doing it in Python, so we're going to do it slightly different, and we're going to use, instead of Excel solver, we're going to use the SciPy minimize module. And the intention is that I'm going to vary the opening of the choke 1 from 0 to 200 and the choke 2 0 to 200, and I'm going to compute the objective function, which can be gas rate, can be revenue, okay, or it can even be condensate. Okay, exactly the same that we have done for the gas lift case. So here I was explaining a bit what you can find, but essentially you have all these equations that I have listed here before, and I say we have one equation that gives you the wellhead performance relationship. Okay, that if I specify the rate, I calculate the available pressure at the wellhead. And then I try to vectorize that equation such that I don't have to apply it for well 1 and well 2, but simply I give a vector as an input, and then I calculate another vector, which is this, the available pressure of well 1 and well 2. Okay, then I discussed the flow line and the pipeline equation, and then I created a function that if I receive a vector, okay, flow line coefficient, is this one, flow line pipeline coefficient. Flow line coefficient has a vector, and then P separator and the rate vector, which has the rate of 1 and 2, is going to give me the required pressure at the discharge of the choke. And this has a bit unfortunate name. I call it wellhead pressure required, but it's essentially the pressure that I need at the discharge of the choke to flow against this separator pressure. Okay. Then I say I have to solve this system of equations all together. Okay, so I say given delta P of the choke, I have to find QG, the rates of well 1 and 2, such that this difference, the the pressure that I obtain here minus the delta P will be equal to this pressure required. Okay? And also the same thing for well 2, the pressure I calculate here available minus the delta P of the choke specified will be equal to the required. Okay? And then I simply, to make that possible, I created an error function where I squared, brought everything to one side such that it will be 0, square it, and then I sum both of them. Okay, so this will be, that's how I'm going to use, okay, that's how I'm going to use the solver. Okay, so it will be, the solver is changing the QG1 and QG2 such that this error, which is P wellhead 1, sorry, minus delta P choke 1 minus delta P W minus, not delta P, not delta P wellhead required of 1 squared plus P wellhead 1 2 minus delta P choke 2 minus P wellhead 2 required will be equal to 0. Okay, or will be, in this case, will be minimize this expression. Okay, so after we define our function, we define our input data that we have. Can maybe duplicate this and put it here. Okay, we input data that is, I hope all of it is in the right units. But you see here, I'm just listing all the data I need to make my calculation. And I have reservoir pressure. I create a vector of reservoir pressure, back pressure or inflow coefficient, back pressure exponent, the S elevation coefficient for the tubing, CT, the tubing coefficient, initial seeds, that's something I need. Every solver usually typically needs some initial values, and I'm saying a very low value, assuming that it's almost closed, that the chokes are almost closed. Pipeline coefficient, flow line 1, flow line 2, separator pressure, and then condensate gas ratio, and that's something we're going to use later, and um, um, oil price and gas price, okay, just to calculate the revenue. Okay, then I do something similar to what was done on the gas lift case. I create number of points. In this case, I'm not going to use 100. I'm going to use much less because this case takes a long time to run. I'm going to say the delta P of choke 1 maximum can be 150. Also the same thing for 2. And create now a vector that goes from 0 delta P to that maximum with these 20 points. Okay, then I make these variables just to store results, the gas rate, condensate, and the rate of well 1 and well 2. And then simply go through each combination. For delta P in that vector, and for delta P in the vector of well 2, you just have to minimize. Okay, so this is the solution. So you have to minimize this error function. Okay, and you're going to change the rate of this is a vector, okay, so this has two values, okay, given all of these arguments, okay, PR, CR, and CTS, CPL, CFL, P separator, and the choke that I specified. Method to solve that, I told you the way we have solved it with Excel before was with bottom hole pressure. In this case, we're solving with rate, and it's actually quite a challenging problem. So I tried with different methods, and this Neldermead was the one that gave the best results. We're going to talk a bit about this method later. Okay, and here for all of these combinations, I'm appending the results, okay, to the solution vector. I'm calculating revenue, and then I'm converting it to plotting everything in million, because for gas, each kind of rate is big, so we want to put everything in million. Going to run up to here. Okay, I'm going to maybe copy. Such that you have it in your notes. Okay, so remember these two guys, they are, okay, delta P choke 1. I have from 0 goes all the way to 150 and has 20 values, and then delta P choke 2, that is here, that is from 0 to 150. And here is solving this error minimizing, that's essentially the solver. Okay, that's like the Excel solver. Okay, and by changing this value here, okay, which is Q gas 1 and Q gas 2. Okay, and last, this is error result collection of results. Okay, and I'm solving and I'm accumulating that in this empty vector. So I'm appending the old vector that has 0 in the first iteration with this and the dot product is simply, I have a dot product of Q gas well 1, Q gas of 2, and then I multiply it times the condensate gas ratio of 1 and the condensate gas ratio of 2, okay, which will be okay, essentially this one times this one plus this one times this one, okay, to calculate the condensate. So then comes the last part, which is the plotting, okay, and here I'm going to say gas rate, that's what we're going to look at first. the objective, but it could be revenue, can be gas, can be condensate, and the constraint. Okay, constraint if it's the gas rate of well 1, gas rate of well 2, or if it's the total gas rate. For some reason, my processing plant cannot take more than some amount of gas. Okay, so I can choose here. First, I leave it to a gas rate of well 1. Okay, I think that was what we had initially. Okay, and we have the objective is the total gas rate. Okay, then I change the size of the figure. I create this mesh that I mentioned before for the rates. Remember what we are plotting here. It's okay, this delta P choke 1, delta P choke 2. So I have to plot to create this mesh. That's what I'm doing here. And then let's, for now, don't plot the contour plot. Okay, just to keep it simple. Contour plot, not going to plot the constraint. I'm simply going to make this color map of delta P choke 1, delta P choke 2, and the objective, which is the total gas rate. Okay, and I'm putting so let's run all, and it's going to take some time. Okay, you see it's still running. This is the cell that already finished, number 3. This is number 4. And it gave me an error that it didn't converge for some combination. Okay, and we're going to see that soon on the chart where it looks like. But as I mentioned, this is a very kind of relatively tricky problem to solve. Remember, if we try to iterate in Excel with Q, the initial seed had to be relatively close to the solution. Okay, otherwise we were going to get a problem in the solver. Okay, we were going to get, this is because of this square root, which if we get a negative number, it like, it disturbs the progress of the solver. Okay, so in this case we have exactly the same, but it's not many points, it's one. Okay, I think. Okay, now it finished, and here is showing the total gas rate, okay, in this color scale, with delta P of choke 1 and delta P of choke 2. Okay, so let me just paste it here. That was why I had it here. And no surprises here. Maybe I didn't need to make any optimization at all to get this result, but essentially we are we're saying that to get maximum total gas production, simply should be in this point. Okay, maximum total gas production. Okay. And then you see that if I keep the choke of 2 open, but then I start to close um, the choke, or I start to close the choke of well 1, then I reach a point where well 1 doesn't contribute anymore. It becomes constant. Okay, you see that this color becomes uniform. That means that 100, this well stops producing apparently between 125, something like that. Okay, it stops producing. And the same thing here, but you see that well 2 has much less impact on the production. If I close it, okay, you see here it remains more or less constant from here, maybe 90, okay. Still the values are quite green, okay. Here the values become very, very low, okay. Therefore, we expect it's like well 1 is more productive than well 2. So if I choke well 1 will have much more impact on the objective function. Okay, and if we look at the data that we had, okay, you see that the pressure, reservoir pressure of well 1 is higher, the productivity of that layer is higher, and then the rest is relatively comparable. The CT of the tubing is actually a bit less, but is comparable. So essentially, well 1 is much more productive. That we can see if we apply the control line. We can see more in detail. We apply control lines. Okay, we are going to make control lines. Remember what will control lines were? I try to join all of these points that have the same value of Qj of gas rate. Okay, in this case I have just one point, but if I go to 4, for example, I might join all of these that have 4. Then I go to 3, maybe all of these that have 4. So we'll see how that region looks like. Okay, contour of the objective. Okay, then I run it again. Okay, and you see that's exactly what we were expecting. Okay, so you see that if I want to get the maximum is here, but if I want to get 4, for example, okay, I can get 4 by different ways, but essentially I can choke completely, or I can choke at 40 bar well 1, and I don't choke well 2, or I choke well 2 at 50 something, 59 and 0, and no choking of well 1. Okay, or I can have everything in between. Okay, so now let's see the effect of the constraint. Okay, um, and this will be effect of constraint gas rate of well 1. Okay, gas rate of well 1. Okay, we say that has to be below a limit. Okay, so we are going to plot the constraint. Now we are going to activate these two lines. Okay, I don't know what happened. For some reason, for some reason it was not working. So again, this is our okay, this is our objective function, which in this case is the total gas rate, depending on the delta P of the choke. So that means if we keep both chokes no delta P, I will get maximum. But now I have here the lines that ISO lines, these are the contour lines of the objective function. That tells me I have here I will have 4, and this is the maximum, okay, which is like 4.5. Okay, and I go reducing as I choke both, okay, on this direction. Okay, but then I have here these brown lines. These are the constraint on the gas rate of well 1. Okay, so for example, here will be the maximum. Okay, if unconstrained. This is if maximum Q gas if unconstrained. Okay, just erase that here. Okay. But now let's say that we have a constraint that Q gas of well 1 has to be less or equal to 1 e to the 6, okay, standard cubic meter per day, due to sand production. Okay, so 1, it will be, here you have 1.2, this is Q gas 1, and you see it's very much impacted by the choke um, sorry, this is well choke of well 2. Okay, sorry, here I should have, here is 1, it should be 1, okay, it should not be 2. Okay, it's like this. Sorry, I was using the wrong okay, the wrong constraint. You have to be sure that you're using the right constraint, which is, I was using here, it should be 1 if it's a well 1, but I was using 2, which is the rate of well 2. Okay. So let me paste it here and send it to back, and then that's the maximum here. Okay. So we have again the same thing, the contour lines of the objective function, that's the maximum if it's unconstrained, okay? But then you have here the lines that are of well 1, okay? Okay, and it doesn't work for some reason. Okay, so here you have 0.8. If I'm choking, you see they are very much affected by the delta P of the choke. If I'm choking at 105, and I will get, I can, depending on the choke of 2, I can get a variety of rates. But essentially, is affected mostly by the delta P, okay, these contour lines. So if I say, let's not use 1, I think 1 is too, not sure if the eraser will work here. No. Okay, let's use, for example, the 2.4 e to the 6. Okay. Then you see is this line. Okay, and in this line you have to find now what is your feasible region. Okay, your feasible region is, it has to be less, right, than that. So if I move in this direction, I open the choke, I will be producing more and more from well 1. So my feasible region essentially is this here. All of this is my feasible region, okay? And then I have to find where is the maximum on that feasible region, okay? So the maximum is here in this case, okay? So that's the maximum QG if constrained by Q gas 1 has to be less or equal than 2.4 e to the 06 standard cubic meter per day. Okay, and it looks like a bit obvious. Simply I leave well 2 fully open, okay, and I choke well 1 until I simply reach that constraint. Okay, I choke well 1 until I simply meet 2.4. Okay, which is like a trivial, I didn't need to do any exploration of the to know that answer. Okay, also for the previous that I simply do both chokes open, that is also like a trivial solution. Okay. Before we finish with this example, let me just do 2 more runs, okay, where we are going to look at the revenue and the condensate. Okay, I don't need to do run again, but I simply need to change here now. My objective will be revenue, okay, and yeah, let's give the well 1 has a constraint. Okay, so now you see that's the revenue. Okay, and revenue now I have to add decimal point 1 because otherwise I won't be able to see what's happening. Okay, so you have 1 million, 0.8 million, 0.5 million, 0.2 million in this region, and you get again maximum revenue when both chokes are fully open. Okay. Okay, what happens now if I say that I want to see the condensate? I want to optimize condensate, which is 3 in this. Okay, and condensate now it can change completely the chart. Okay, and that's because in the condensate, let's go back to our CGR where we had the input data. Okay, CGR of 1 is not producing any condensate. Okay, but C2 is producing a lot of condensate. Okay, so simply the solution again, which might be logical, I have to choke as much as possible well 1, okay, and then I don't choke well 2 at all. And that's where I get maximum condensate production. Okay, then just to finalize this example and this class, I want to see what happens with depletion. So just if I change now, let's say well 2, they are producing from different layers. Okay, so well 2 has been depleted now to 150. Again, I'm going to generate exactly the same plot. So I have to run all of them. While we wait when it runs, I just want to show you this string because everything here, the color seems quite uniform. Okay, it's following the same trend, but this square here actually you see has a different color. And that's probably because here it didn't converge properly, the optimizer. Okay, so that's related to this warning that we get that one point didn't converge. Okay, this warning here. Still have to wait a bit for it to get the results. Okay, finally it finished, and that's the result. In the condensate, you see that also the maximum didn't change. The location of the maximum didn't change. Effect of depletion, paste it here. Okay, and then I'm going to put just the other one next to it for comparison. Okay, but on this one, but the one to the right, this P R2 was, I think was like 210 bar, while PR2 here is 150 bar. Okay, so you see in that case simply shrinked the the now the revenue that you get is not the condensate that you get is not as high, it's not 500, almost 600, but it's actually closer to 325. Okay, but essentially the location of the maximum point didn't change much. Okay, bye.